Come on, recording. Okay. Now, today we're getting into a new chapter. On iterative methods, and today we're going to focus just on one particular iterative method for solving ax equals b, where a is assumed to be symmetric positive definite. But before I get into that, I want to say a few words about why iterative methods. So what we've seen so far, the Gaussian elimination and variants on it, such as Cholesky decomposition in the case of symmetric positive definite A. These are examples of what are called direct methods for solving ax equals b. And for this chapter, we're back in the case of A is n by n, it's a square matrix, invertible, unlike what we're just dealing with in the last chapter of least squares. Now, for a general case, Gaussian elimination, with, partial pivoting is the way to go. And then there's certain special cases where you do something different. But there are very good reasons to not use direct methods. So in other words, I'm going to, after teaching you all about direct methods, I'm now going to explain to you what's awful about them, and instead use what are called iterative methods. Now, I'm not saying we shouldn't use direct methods. There are cases where they are the best option, but there are certain important situations where we ought to do something different if we can, and that's what iterative methods are for. Okay. What if you already have a good approximate solution already for some reason? Something that's dependent on the application in which you're solving ax equals b. So you have something that's already in the ballpark, and you just want to improve it to get a highly accurate solution of ax equals b. Well, Gaussian elimination and methods like it they don't let you take advantage of that extra information that you have. There's no way. It's not a mechanism. There's no mechanism for taking a known guess and refining it. So that's reason number one. Second, what if you don't really need high accuracy? Like, what if you only need a solution that has accuracy within 1%? And this is especially the case if the ingredients of your system, if A and B, have errors in them. Like, suppose A and B result from some measurements, and maybe those measurements are not very precise, or maybe there's a lot of uncertainty. Uncertainty quantification is a big deal in math. It's one of those things like machine learning. These are the areas of math we're supposed to care more about now. I roll. So if there's a lot of uncertainty in your model that your ax equals b comes from, there's no point in trying to get a solution that's fully accurate except for round-off error, like getting 15 decimal places correct, when you already have some error in your model that's much larger than that. So direct methods have no way to stop early. With direct methods, you have to see the entire process all the way through to the end. and get your solution that's going to be highly accurate for that A and B, hopefully. There's no way to do less work in exchange for less accuracy. Okay. Okay. So this could be inefficient. Like, what if you don't really want to spend a whole lot of time um, solving a system when you don't want that much accuracy? You're forced to spend time you maybe don't want to spend. Okay, third reason. What if a matrix is sparse? Now, we saw an example of this already with banded matrices, but there are other kinds of matrices that may not be banded, but they're sparse. They still have mostly zero entries. So Gaussian elimination, and especially with pivoting, can destroy sparsity. So A may be mostly zero entries, but then you do PA equals LU, your LU decomposition, and your L and U factors might be full matrices, might be dense. So for matrices, the opposite of sparse is dense. So dense matrix is one that has mostly non-zero entries. And generally, you still want to do pivoting if you can, because it helps contain round-off error, but you might end up losing efficiency. Okay. All right. And finally, what if you don't really have A? What I mean is, as a 2D array that we're accustomed to, where you have a two-dimensional array of all the entries, A11, A12, etc. A might be represented implicitly by a function y equals some function of x where that is just equal to the matrix vector product. So you may have a function where you can input any vector x and the output will be A times x. Now that's not so good for Gaussian elimination, because Gaussian elimination works with the individual entries of a matrix. So it'd be nice to have some way of solving Ax equals B where you don't have to manipulate individual entries like Gaussian elimination does. Okay. So can we solve Ax equals B using matrix vector multiplication? And what we'll see in this chapter is the answer is yes. So these are some very compelling reasons, at least some situations, to not use direct methods. So iterative methods are a nice alternative to that. Okay. Now, there are two types of iterative methods. Okay. Let me make sure I get my notation straight. Okay. Okay. So first we have a stationary iterative method. And it's a method of this form, where we have a new iterate. So I'm going to, throughout this chapter, I'm going to use this notation where I have a superscript to refer to the iteration number, and it'll always be in parentheses. So it's not something you could confuse with an exponent. So any iteration that you can write in this form, where the new iterate is some function of the old iterate, for some function g. Now, I'm not actually covering these in this class. They're in section 5.1 of the book. If you took 561 with me last year, they were covered then. So some examples are the Jacobi method, Gauss-Seidel. That's probably most often used. Also SOR, which is stands for successive over relaxation. And all these methods are very closely related. What's interesting about SOR is it was actually developed by a PhD student for his dissertation, David Young, back in 1950. So somebody to make every numerical analysis PhD student from then on feel like a schlub, or feel like an underachiever. Okay, so and that dissertation actually can be found online. Okay. Okay. If you wanted to take a look at it. What's funny, if you look at old papers, they used an ordinary typewriter for them, and somehow would deal with the math symbols, which would have been particularly onerous. And it's actually kind of painful to read, at least to me anyway. Although I think what was done with this dissertation was it was like reformatted, sort of like a modern LaTeX document, to make it easier to read. Okay. Now, this is an example of what is called fixed point iteration. Because you want to make sure or have some understanding of when this kind of iteration would converge. And this is an example of fixed point iteration. So I'll have a theory about fixed point iteration. There's always a section in my book for everything, I guess. To have some understanding of this for specific iterative methods. Okay, so that's the kind of method I'm not going to be covering. And then we have, well, there's stationary, then there's non-stationary. So the idea there is find what is called a search direction. So to go from one iterative to the next, you need to find out which direction do you want to go in. And there's different criteria for what constitutes some sort of ideal direction. And you form what is, and now once you have a direction, well, how far do you go in that direction? That's where line search comes in, and I'll illustrate it with that method I'm going to show you today. All right. So non-stationary method is a method of that form. It can't easily be expressed as a fixed point iteration. And that's what the rest of chapter 5, so sections 5.2 and 5.3 are about. So this includes what are called Krylov subspace methods, which so I took some ideas from there to develop Krylov subspace spectral methods for PDEs, but that's a whole other kind of animal. Okay. But Krylov subspace methods are what I'll show you, not today, but next week. Okay. So what I'll show you now is the simplest non-stationary method. Okay. Let's see. Start doing a little quick editing of the notes. So this makes things a little more precise. So the non-stationary method is something of this form. So this notation I'll use. Here's our previous iterate. Here is our search direction. And we'd like it to somehow be parallel to the error. Like here's where we are now. Here's the exact solution we're trying to get to. So this is the ideal search direction, but we have no way of knowing it because X is what we're looking for. But if we can find a search direction that in some sense would be in this close to this direction, that would be great. Then we figure out how far to go along that direction, and that's how we find the parameter alpha k to try to make the new iterate closer to the exact solution x. Actually, let me fill this into my notes. So x refer to the exact solution of ax equals b. Okay. All right, so that takes us to steepest descent. Now, steepest descent is only for the case where A is known to be symmetric, positive, definite. And what we're going to do is we're going to treat the problem of solving ax equals b by trying to find a minimum of this function. So 1/2 x transpose ax minus b transpose x. Now, where would this function come from? Well, use your multivariable calculus. If you want to find a minimum of this function, you take the gradient. So a gradient of our function phi is equal to a x minus b. All right. One thing I have to be careful about here. I want to refresh my memory as to which problems from this section I have assigned. Okay, good, not this one. All right. And the Hessian, so matrix of second partial derivatives of phi, basically you're taking the derivative of this, and this will just give you A. Now you can see where this comes from here. If you think of this as the case n equals 1, so x is just a number. So this is 1/2 ax squared minus bx. But when you take a derivative of that with respect to x, and you get ax minus b. Take a derivative of this with respect to x, and you get a. Okay. Now, whoops. So to review your multivariable calculus, because I'm sure it's been a minute since you've taken that, that a local minimum occurs when the gradient is 0, or the 0 vector. So ax equals b. And the Hessian at a critical point, wherever gradient is 0, the Hessian is going to be symmetric just by its definition. But if it's also positive definite, that is a local minimum. And it can actually be shown that the solution of ax equals b is not only gives you a local minimum, it's a global minimum. So it's the only critical point of this function, because the solution is unique due to a being positive definite. So it can be shown that this is a global minimizer of the function phi. All right. So we could design a method around trying to make this function smaller, knowing that as we make phi smaller, we're making progress towards where it's minimized, which would be the solution to ax equals b. Okay. So if we have any vector, like an initial guess, then also for multivariable calculus, minus the gradient is called the direction of steepest descent. So if you go in this direction that will make a value of phi smaller as rapidly as possible. So that would be a vector b minus ax naught, and this is called the residual vector. Now we've seen that before from least squares. That if you have any vector x, b minus ax is residual of a system ax equals b. So because its direction of steepest descent, because it's going in its direction will make the value of phi smaller, that makes this residual vector a logical choice for a search direction. So we choose. So at each iterate xk, we compute a residual vector, and we call that our search direction. So pk is equal to rk. So now all we have to do is we have to choose our new iterate. It'll be of this form. It's our old iterate plus a constant times the search direction. So we want to choose this constant alpha k to make this as small as possible, because that's what we're trying to do. We're trying to minimize this. So what we've done here is we've changed a multivariable minimization problem of minimizing phi for all x in Rn to a one-dimensional minimization problem. It's because we've now decided that our new x will be of this form, dependent only on a single number, single unknown parameter alpha k. So you can think of this as a function of one variable, and we want to choose the value of that variable to make this as small as possible. Okay. So so now that we've established we need to solve a single variable minimization problem, that is actually a subject of a homework problem, but because I have not assigned it, I'm just going to have a joy of working it out for you. Okay. To solve this, I'm going to define a function of one variable. So I'm going to call it g of alpha k. Actually, I'm just going to call it g of alpha just to have a notation less cluttered. And that will be equal to phi of xk plus alpha times rk. Okay, so I'm going to solve this minimization problem as you would in single variable calculus. I'm going to take a derivative of this with respect to alpha, and then set it equal to 0, and find a critical point alpha. Okay. All right. So what we have here is okay. All right. So g prime of alpha. So that's going to be equal to, I can use a chain rule here, because here we have a function phi of n variables, but what's plugged in here is a function of one variable. So by multivariable chain rule, this would be equal to, whoops, stop that. Okay. The gradient of phi evaluated at this same point, so I'll plug that in there. So derivative of the outer function evaluated at the inner function. As you may remember, chain rule being taught to you. And then we take the dot product of that with the derivative of what's inside with respect to alpha. Okay. Now, for gradient of phi, well, that's given up here. It's ax minus b. So, oh, before I continue, though, I have a definition stated earlier, but I want to have it right here. The definition of RK, because I'm going to need that in a little bit. Okay. All right. So I fill in what the gradient of phi is. So that would be b minus a times whatever is plugged in here. So I'm going to fill that in. Okay. Dot product with the derivative of this with respect to alpha. Well, alpha is only showing up here, so the derivative of this is just RK. Now here we have a dot product of this vector with this vector. So I'm going to write it this way as a transpose. Okay. Since that's how you write a dot product. Okay. Now, do a little algebra here. So I'm going to distribute the A through all this. All right, so then I have AXK and then alpha ARK. All right, let's take down these parentheses. Okay. Now, B minus AXK, that's RK. That's why I want to have it right here. So I'll just go ahead and make that substitution. Okay. Now I can apply this transpose to all of these, or these two terms. Okay. All right, so RK transpose. And then here I have ARK, that whole thing, transpose. Okay. All right, then I'll distribute the RK on the outside. Okay. And then, very important property of transpose that comes up, I've feel like I've used it in class a number of times already. Transpose of a product is a product of a transposes in reverse order. All right, so that's going to be RK transpose A transpose RK, but A is assumed to be symmetric. So A equals A transpose. Okay, I don't need the parentheses anymore. And I'll take away that transpose from A. All right, so now we're done. This is our derivative in its simplest form. So a critical point occurs at, I'll call this alpha k. That's a parameter I'm looking for. So I just set this equal to so I set this equal to 0 and solve for alpha. And just get this expression. Okay, so I have this in the denominator and this in the numerator. Okay. All right. Now, how do we know if this is a minimum or as opposed to a maximum, or maybe neither one, like maybe some kind of inflection point? Well, from my derivative, recall, so if anyone remembers their Cal 1, what would I do with this to confirm that this is actually a local minimum?
Take the second derivative.
Yeah. So G double prime okay. Wait, something seems odd here because this isn't actually going the way I want to. Unless I have some kind of mistake. And this expression is the correct expression for alpha k. All right, I go back here, and yeah, that certainly is. Oh, okay. There is a mistake. I filled in b minus ax. That is a residual. That is the direction of steepest descent, but that is minus the gradient. I have these terms in the wrong order. So I'm going to have to go back and fix that. Dang it. Okay. But then again, at least it's not a mistake in the book. However, there's still time to find one of those. All right. So, and I know I could do this a lazy way and just put minuses in front of every term. And I actually had a professor do that once when discovering he made a mistake. Okay, so this is a plus. Okay, so now we have alpha RK, and then this is minus the residual. So, and basically everything here is going to be negated. Okay. Whoops. All right. Sorry, just bear with me for a bit. I want my notes to be as they should be. Okay. Oh, well, I could have got rid of these parentheses a long time ago. Okay. All right. Yeah, so now a second derivative will just be, well, it's multiplying alpha. It's a linear function of alpha. Okay. All right. Now, to have a local minimum, what has to be true of what should be true of a second derivative?
Isn't it greater than 0?
Yeah, it should be the second derivative at a critical point, if positive, tells you it's a local minimum. How do we know that this is positive? What do we know about A?
Asymmetric positive.
Yeah, symmetric positive definite. So by definition of symmetric positive definite, this is guaranteed as long as residual is non-zero. Well, if residual was 0, we'd be done. So as long as residual is non-zero, this will be positive, so that's the local minimum. And the other thing I want to point out is alpha k is a fraction. How do we know we won't divide by 0? Well, that's the same thing. We know that the denominator here is going to be positive. So there's no need to worry about that. Okay. All right. So any questions about what happened here in terms of finding alpha k? All right. So now that we have that detail worked out, we have a search directions, and we have once the direction is chosen, we know how far to go along that direction to make the most progress towards the solution, or a minimizer of phi. So now I can show you the whole algorithm. And it turns out there's not really that much to it. So A must be symmetric positive definite. We choose our initial guess. And if you're not sure how to choose it, you can always just choose it to be 0. So for each iteration, compute a residual, which is minus the gradient, compute alpha k, and now you compute your new iterate from your search direction and how far you go in that direction. And that's it. So, and then you apply some convergence tests, like if the difference between iterates is very small, or maybe if a residual is very small, those would be good criteria for stopping the iteration. But this iteration is guaranteed to at least make progress towards the solution. But it doesn't always work well. So what I'm going to do is actually, I'll talk about it a little bit, but first I want to show you what can go wrong with it. So I'm going to unshare here and go over to MATLAB. Okay. Okay. So I have some code here that's going to perform a demonstration of steepest descent on a couple of 2x2 symmetric positive definite systems, because that way you can visualize what's going on. And even in a 2x2 case, you can find a situation where steepest descent performs badly. Unfortunately, it would not be a good idea for me to post all of the code for this demonstration because that includes implementing a method of steepest descent, and that's one of the homework problems. So sorry about that, but at least I can show you some nice plots. Okay, so for the first example, the matrix A is constructed to be well conditioned. So steepest descent will work well in this case. Now, what I have here is a plot of a function phi of x, because we're trying to find a minimum. And what we see here, if this is a function, if I turn this graph around, here's, you can see that there's a minimum down as well. So here's at the bottom is where the exact solution is. Now over here, I have a contour plot of phi. And so here's the origin. So that's my initial guess, 0, 0. Over here is the exact solution, which happens to be 2 and minus 2. So I'm going to show you the progress from my initial guess to the exact solution. Okay, so here we have our first iterate. Actually, I'll try to make a plot. I want to have as much as possible equal scaling between x and y. Okay, so here's my first iterate. Now, based on the contour plot, the value of phi is lower, so that's good. We're getting closer to the minimum. And now I take another iteration. Notice it's perpendicular. That's actually a property of steepest descent. Each search direction, each residual, is orthogonal to the previous residual. Now, if I take another step, you see we're getting closer. All right, getting closer still. And notice there's a zigzag pattern. And that's because not just the fact that each direction is orthogonal to the previous one, but this is 2-dimensional. This is 2D. There are only 2 directions to choose that are orthogonal. So if this direction is orthogonal to the previous one, it'll be parallel to the direction that's 2 back. So alternating directions are parallel. So you see it's getting closer, and at least it's converging. And we see that it's doing this zigzag thing here. All right, so this is when it's well conditioned. I don't know if you can see down here. Here's a measure of the error. It's getting smaller, and pretty soon I'll have it stop. So then I can show you the next example. I think when it gets below 10 to the minus 3 or so, it'll stop. Yes. Okay. Here is an ill-conditioned 2x2 matrix. Once again, here is the origin, the initial guess. Here's the exact solution. Notice the different shape of the graph of phi. Because in the previous one, there's a very well-defined minimum. But here, it's like a trough. Or it's almost like a comparison I make is well-conditioned versus ill-conditioned is like a bowl versus a gravy boat. So yes, there is a minimum, but look at the level curves. There are these really long, elongated hyperellipsoids in n-dimensional space. So, so around the minimum, the surface in this direction is a whole lot flatter than in the previous example. So that makes it difficult to get to the minimum. So now if I do the same thing, breaking progress from the initial guess to the exact solution. Okay. Oh, let's see. I don't want to rotate. Okay. I don't know if you can see. Stop it. That the steps are really small, and every other step is so small you can barely see it. And in fact, even these steps that it's taking, that's that's actually leading to a close the distance between the current iterative exact solution, those steps are getting a bit smaller too. And if you look down here at the error, yeah, it's getting smaller, but very slowly. So at some point, it gets kind of painful to watch because you can tell, look at the circles. They're getting closer together. In other words, the progress is slowing. And this is for a 2x2 system, so that's really kind of sad that this method requires so many iterations to get anywhere near the solution. So here we have a clear contrast between the behavior for a well-conditioned matrix and an ill-conditioned one. Now, while I should not show you the actual steepest descent code, what I can show you is how I set up the examples to create these cases. Okay. I think I can. This is, like, you want to root for it to get there, but at some point you just, shaking your head. This is, okay. So, all right, enough. Yeah, here the error is like still a 0.02 roughly. Now, if I open up the main function, okay. So for a well-conditioned case, here's my matrix 3, 2, 2, 6, and here's my vector b. And when I call my SD contour function, actually performs steepest descent and does all the plotting. Here, I made up an orthogonal matrix, and then, and actually the columns of this matrix would be the eigenvectors of A. Here I have a diagonal matrix that has 1 and 1,000. So because of the difference in orders of magnitude between these are the two eigenvalues, which, by the way, are also singular values. Only if A is symmetric positive definite, the eigenvalues and the singular values are the same. And remember, a condition number is ratio of largest singular value to smallest. So the ratio here is 1,000. So it's not even all that badly conditioned, but kind of bad. And then I make a matrix A, Q, D, Q transpose. You can actually think of this as a singular value decomposition of A because it's symmetric positive definite. So in fact, because when you have a symmetric matrix, the left and right singular vectors are the same. So this is like playing a role of U sigma V transpose. Okay. So that's how I constructed a matrix to be ill-conditioned. I forced it to have eigenvalues or singular values with very, very different orders of magnitude, and that made it ill-conditioned. So there's various ways of contriving examples like this to make certain bad things happen. Okay, so what I was just showing you there. All right. So yeah, so when A is well conditioned, it actually works pretty well. But because of level curves of phi and how they behave when A is ill conditioned, you saw it right there that the iterates progress very slowly towards the exact solution. And here's the other problem that was spotlighted there. Yes, each search direction is orthogonal to the previous one. You actually, one of the homework problems from this section is to prove this. That each RK plus 1 transpose RK is equal to 0. And using his formula, because each residual is defined in terms of a corresponding x. And here you have xk plus 1 in terms of xk. That makes it possible to define RK plus 1 in terms of RK to show, and then take their dot product and show that it's 0. But the thing is, okay, each direction is completely independent of a previous one, but what about directions before that? You want each iteration to be covering completely new ground if possible. Like if you could have each search direction orthogonal not just to the previous one, but all previous ones, that would be great. And other iterative methods that I will be covering like next week will be based on that idea and trying to have more independence of all the search directions, not just the previous one. Okay, and this text I have right here just describes what I showed you. Okay. All right. So in fact, one of the homework problems will be to basically implement, be able to show this case yourself. I'm not asking you to do the plotting, although it would be cool to learn how to do all that. And what I may do at some point, like after this assignment, after you've done actual steepest descent, like for the homework, is put out the code that does the graphics so you can see how that's done. Okay. So now that I've come to the end of the new stuff, okay. Does anyone have any questions about this or about any ongoing homework?
I have one question.
Yeah.
So we said the direction of steepest descent is negative gradient. I'm not sure why we said that though. Like,
Oh, okay. Like, so where does that idea come from?
yeah.
Okay. So, all right. So, all right. So first, an idea from multivariable calculus. The directional derivative of some function phi. So instead of just taking partial derivatives with respect to like x1, x2, etc., you want to find out what is the rate of change of phi when x is changing in a direction indicated by u. So that would be so sometimes written as d sub u of phi, and that is equal to the gradient of phi dot product with u. Okay. But that is equal to the magnitude of the gradient, like in the two norm sense. Okay, actually, I need to stipulate that u is a unit vector. So the dot product would be a gradient of phi, magnitude, times the magnitude of u, which is 1, and then times cosine theta, where theta is the angle between the gradient and the direction of a derivative. So the idea is we want the greatest possible decrease. So we want this to be the most negative possible. So this is minimized if cosine theta is equal to -1. So that would mean that so U would be chosen to be a vector pointing in the opposite direction of the gradient. So we choose U to be minus the gradient over its magnitude. Then the directional derivative turns out to be minus the magnitude. So this is how we so then so that's the direction of steepest descent. If we make this a plus sign, that's the most rapid increase. So we're taking a derivative in the opposite direction. And then if the gradient, if U is chosen to be orthogonal to the gradient, then the directional derivative is 0, and that defines a level curve or level set of phi. Actually, let me fill in one last detail here. Whoops. Okay. Yeah, so that's the best angle to go with for decrease.
So, in this case now, we didn't have the norm of the gradient. We just have negative of the gradient. Are we assuming the norm of the gradient is 1?
Oh, okay.
Because our U here has norm of the gradient as the denominator.
Yeah. Oh, yeah, to make sure that U is a unit vector.
Oh, I see.
So then so this will be the rate of change of phi in this direction.
Okay.
Oh, oops, I need a phi there. Okay. Other questions? We still have 9 minutes. Okay, I will stop recording at this point.